Hello everyone, welcome to day 5 of Avalon game project. So after 4 days of non-stop writing documents, today we finally going to write some code, not a lot, some. And it's also and it's still pretty high level, and I swear I can explain. Okay, so before we start, let's introduce some jargon first. These seems to be big words, but in reality, they are just some very simple ideas. Okay, let's start with a state machine. So when I first heard this name, I was uh, it sounds scary to me, like a machine and it has states. Wow, what is it? Um, and it's a mathematical model. It's to anyone who haven't really implemented something like it sounds really scary. But in reality, it's just a bunch of code designed in a way that, um, given a code which always represent a state, and the number of state is finite, so it can be uh, a state machine. Well, a finite state machine cannot have infinite number of states, so it's also called a FSM, finite state machine. So it only have uh, one of a finite number of states at a given time, and this machine transitions from one state to another based on events, inputs and events. Um, and another very important characteristic about a finite state machine is that given the exact same number and order of events, it should end up in the same exact state. So it should be reproducible. Why do we need to introduce this idea? I'll explain later. But let's bear with me. You don't have to understand this for now. It's just a big word. I swear, when you see the implementation, you'll be like, "Oh, really? You give this thing such a scary name?" Um, okay. So the next a term we're going to introduce today is dependency injection and inversion of control. And of course, we abbreviate it as DI and IOC. So what is this? It is really, instead of an object, or instead of basically managing its own dependencies, we injected these dependencies to these objects. Okay, sounds scary. Real life example, a motherboard. I'm sure whoever is watching this video must know what a motherboard is. If you don't, pause the video, go Google it, so that this example makes sense to you. Okay, so a motherboard. When we buy a motherboard, it contains almost nothing. We have to, well, a single motherboard won't work at all. We will have to buy CPU, RAM, disks, and oftentimes video card. Well, nowadays the CPU comes with video processing, but bear with me. Let's not get into details. So a motherboard only works if you provided those devices or those pieces. So a motherboard, so we connect everything to a motherboard. We turn on the power, and the motherboard just basically distributes everything. It looks for the booting information from the disk, then load it into memory, then send all those instructions to the CPU, and while sending the instructions to the video card for it to translate all the good stuff into pictures so that well human recognizable pictures. So this is a form of dependency injection and inversion control. So 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 what really is this? So we inject the CPU, the memory, the disk, the video card into the motherboard. Motherboard only provides an interface. So as long as your CPU is compatible with the CPU socket I provide, I'm going to be able to work with you. So whether the CPU is fast or slow, it is not the motherboard's concern. It only cares about what it does, and it only cares about what a motherboard should do with the devices provided to it. So what's an example of motherboard not using dependency injection or inversion control? It would be you have a whole thing with CPU weld on, memory weld on. So basically, you get a humongous one single piece of one single piece of device which contains everything in it, and it manages all those stuff by itself. So, well, basically a Mac. No, just kidding. I use a Mac. But anyways, so I hope this example makes sense to you. So, dependency injection and inversion of control, they are also big words. It's just, so the core idea is that every single piece only care about it, the piece, the logic of itself. Everything else, you put it in, and everything else, it just doesn't care. It uses whatever is provided to it. And we're going to see an example of it just today. Bear with me. Since we talked about interface, I'm going to introduce two more concepts here, interface and abstract class. These two concepts are often asked in technical interviews, especially for junior developers. It is also often used by non-technical HR people for screening, for the phone screening. It's strange. So they'll ask you, okay, what's the difference of an interface and abstract class? Even though they don't understand it, actually, I've seen a non-technical HR person have a list of questions and some keywords. They just ask the question and look and trying to match whatever you answer with the answer they were provided. So I remember back in 2017 or 2018-ish, I think Java 7 or Java 8 just came out, and from that version, Java interfaces allowed static method implementation. So an HR person asked me about this question, and I gave him a very detailed answer of what's the difference. And he didn't really like it. So that's a funny story. But okay, the thing is, I think it's always to remind everybody what's the difference of these two. So an interface is, the official definition is a shared boundary or contract defines a set method. But in reality, interface is, think the word contract is perfect for describing an interface. So in real life, what is an interface? I think the power socket is a great example. Um, so it defines what kind of a device can be plugged in. It doesn't really care. Well, once plugged in, there's no guarantee for for there's no guarantee for you that there's power coming out of the socket. What it only does, is making sure it only connects to the compatible uh, devices. And that's the only thing it does. Same as the interface. So imagine, um, imagine we are, so yeah, this is an example often used in Java books. So imagine we are a software company, and what we sell to our customers is packages and software. So basically, is something that they can import and use. Um, but we want to constantly making changes to our stuff so that it can be improved, it can be faster, it can use less memory. Um, but we want to make absolutely sure that no matter what we change, it does not affect our customers. So we just provide something just like a socket, like a power socket. So as long as we don't change that and they don't change their stuff, we'll always be able to work together and nothing's gonna break. And same principle applies even within a same company, maybe between two teams. Like maybe your team, like maybe A team depends on something that B team owns or works on. Um, so if something is under constant development, things is bound to change. To make sure that Team B's change won't affect Team A. So Team A could just develop once and just waiting for the good stuff instead of having to worry about changes that B team constantly deliver. And they are going to define a contract uh, between the two teams, like how am I going to use your software, which kind of like what is the input, what is the order of the input, and what is the output, what is the type, the structure of the output. It's all defined in their interface. And again, this is only about contract. It has nothing, absolutely nothing to do with implementation. The, on the other hand, abstract class is different from interface. Abstract class, by definition, it can have its own method. It can have its own implementation. Also, in programming books, abstract classes are often described as blueprint. And I think a good real life example is that um, I think the concept person in real life can be is pretty close as an abstract class, because you can't really make a person. Like every single individual is a person, but you can't just create this general being and general being of person. It's just a concept. A concept contains some implementation or some details. For example, we expect a person to have a heart, to have a head, things like that, to be able to breathe, to have a brain. But everybody's different. Like somebody have big heads, somebody have smaller heads. Um, some are taller, some are shorter. It has some details, but not everything. So to make this concrete, you'll have to, well, in programming languages, you'll have to inherit an abstract class to make it real, to make an object. So in this case, I am a person with, well, average height, uh, bigger than average head, not proud of it, and such and such. So for abstract classes, it's a blueprint. It's really a blueprint for for developers to later to add on more details. So if you really want to, so during technical interviews, I think I know this. Well, at least it was very confusing to me when I first started learning how to code. So I think to people who are new to this industry, I think what I can leave you is that just remember interface has no implementation at all. It's all about the contract, while abstract class has some implementation, or just think about it as some details. Okay, so with that being said, let's really dive into the good stuff. As promised, we are going to do some coding today. Yesterday we have defined the states and the events and the states. We have all the good tables. Oh yeah, we have the models. We have the events. We have even the nice drawing of our state machine. And so today, finally, we're going to implement it. So again, we always want to go top down. And as I mentioned, kill myself, dependency injection, and the inversion control. So we want to come up with a state machine, and its only concern should be managing the state. It shouldn't care about where it is deployed, what kind of a database it uses. So as a core logic of this game, we want to provide something that it should be able to work with. It should be able to work with any database and deployed to any environment. As how are we going to? So this, remember, like we mentioned in the first class that the word soft in software means it is flexible, it is configurable. So this is how we are going to achieve it, by not caring at all of how things are outside of our boundary, by dependency injection and inversion control. So yeah, I wrote something down, but let's just take a look at this very simple example of the state machine. Don't worry about all these warnings, because we haven't implemented everything. That's why. So a state machine. Um, so how? So first of all, we explain what a state machine is. It is just a bunch of code with so by given the same events in the same order, it generates a predictable result. Um, it's perfect for this Avalon game um, because the game rule is set with the same exact votes and with the same exact votes and people's choices, we can be absolutely sure what the game state is, no matter how many times we process those events. So that's how we're going to implement a state machine. A state machine, of course, contains a state. And remember, we also said the state machine changes its states by handling event, and this is how we do it. So this is very simple state machine. So it only cares about building all these states, which we haven't implemented yet. We will do that later. And we are going to, all it has to do is basically build the states, build the state, get the state, and pass in and pass the event received to that state so that actually it so yeah, anyways, so here we really should do something more, but I am going to actually delete this line so that we are not distracted by details. Okay, so we're gonna work with state machine for the next couple of days, so I won't dwell too long on this. What I want to show you is this service repository entity hierarchy. So because I really wanted to explain to you what dependency injection is. For example, the game service. For game service, we want it to handle all the high level game logic. So get game, of course, is one, but another thing I can think of is create game, of course. Thank you, AI. And we have something we should have. Update game is also something. Yes. Update game. I'm actually thinking about start game. So remember, when we start the game, a couple of things we want to do. First of all, we want. So actually, let's write this down. When start a game, so we want to update the game state to in progress or started. 2, we are going to broadcast the game has started. 3, we want to notify the players, their role, and known players. And four, do we have a four? When we start a game, Yep, that's pretty much it. We're not talking about missions and rounds. That's again a separate concern. So to do these, the first item will need to interact with the database, and these two will have to interact with the WebSocket service, the WebSocket endpoint. So remember that again, we only want to, so within the core logic, we only want to care about things that we do have control over. So in this case, at least in the game service, we're going to push down the actual implementation to game repository, so that it doesn't matter if we use DynamoDB or MySQL or Postgres. So for game service, those are irrelevant. So that's, and how are we going to achieve this? That is to, instead of letting game service to choose which kind of implementation it should use, we actually give the implementation to the game service, so that game service doesn't really care about what kind of implementation the game repository has, as long as it gives it a game repository and the game repository has this kind of interface. It is able to use the game repository to find a game. So I hope this explains the dependency injection. As you can see here, also here, state machine, it doesn't instantiate, it doesn't create game service itself, because it should not manage the service, because the state machine should only care about the game state. So but the game state does have some side effect. For example, when the game changed from not started to started, it must trigger something. It must so this state change must trigger some subsequent events, and this kind of complexity is pushed down to game service, so that when we actually start a game, we are going to call the start game, then subsequently the game service is going to basically break down the logic of interacting with the database in broadcasting the game started and notifying everybody their roles to basically divide the complexity even smaller and push down the actual implementations as far as possible. So this is how we achieve the soft part in software. I understand today's things are very abstract, um, pun intended. Um, but bear with me for the next couple of days. You'll see more and more, and I swear it's gonna make more sense then. Okay, so as usual, let's just do a recap. Remember, interface is about contract, abstract class is about a blueprint, and when you whatever you deliver, whatever you're writing or working on, break a big problem into smaller ones and cater and deal with one small problem at a time and make it as isolated as possible. So if when you realize that you are doing too much in one place, it's probably it's a good warning. It's a good sign that you might have just you might got too ambitious, might just put too many things together trying to solve too many problems at once. A good way to remind ourselves about this is by writing unit tests. So a clean unit of well-designed, well-isolated piece of code or a component should be very, very easily tested. And if you are feeling friction and resistance while you're writing unit tests, that's a good sign that your stuff, your component is not isolated enough. We are going to start doing that tomorrow, and it also has a very fancy name of TDD, test-driven design. It's nice. Many people claim that once they start doing it, they could never go back. I myself don't feel that strong about it, but let's see how it goes. I think it's a good practice, a good discipline. It is highly recommended by all those very famous software engineers. So yeah, I'm sure they have their reasons, and I believe I have trust in them enough for me to put some time and try their well-praised approach. Okay, so I know today is a little bit abstract. Well, let's continue this tomorrow. See you everyone. Bye.